So today we have a nice algebraic inequality. We have to prove that a upon square root of b plus b upon square root of a is always greater than or equals to square root of a plus square root of b, where a and b are positive real numbers. So this is Anmol Mishra, and now let us see the solution. How can we prove this particular inequality? So first of all, look at this inequality very carefully. The right hand side of this inequality looks very simple, whereas the left hand side looks a bit more complex. So I will try to just modify the left hand side so we get a nice thing over here. So I write down the left hand side, that is a upon square root of b plus b upon square root of a. So we'll start the modification by taking the LCM. So I'll try to take the common LCM as square root of a b. So here we already have square root of b, so I need to multiply square root of a. And here we have square root of a, so I need to multiply square root of b. So I finally get a square root of a plus b square root of b in the numerator part. Okay. Now we'll discuss something else. Suppose you take a plus b and multiply it with square root of a plus square root of b. The product will give us a square root of a plus a square root of b plus b square root of a plus b square root of b. This is the thing that we get after opening the brackets over here. Now what if with this bracket I subtract a square root of b and subtract b square root of a? If I take this as a complete thing, so after opening the bracket I need to even subtract the rest of the things, that is minus a root b minus b root a. So we can see that a root b, negative a root b, positive b root a and negative b root a got cancelled out. So what we get is a square root of a plus b square root of b. We get this particular thing after we simplify this thing over here. So look carefully that the numerator part over here is a square root of a plus b square root of b, that is over here, and this thing is also equals to this. So the numerator part can just be replaced with this particular value, that is a plus b multiplied with square root of a plus square root of b minus a square root of b minus b square root of a. This thing will also give us a root a plus b root b, and this thing is getting divided by square root of a b. Okay. Now from these two terms I can take negative square root of ab common. So if I take negative square root of ab common, so inside the bracket I will get square root of a plus square root of b. Let's open the bracket and see. So negative square root of a square root of a becomes complete a, and square root of b as it is. Negative square root of b and square root of b becomes complete b, and square root of a as it is. So you can see that we got the same two terms after opening this bracket. This means this bracket is absolutely correct. So let us replace these two terms with this bracket, that is negative square root of ab multiplied with square root of a plus square root of b. Now this complete term is also getting multiplied with square root of a plus square root of b, and this term is also getting multiplied with square root of a plus square root of b. So I can take square root of a plus square root of b as a common bracket, and inside I will have a plus b minus square root of ab, and this thing is getting divided by square root of ab. Okay, we reach this particular step. Now we have to take the help of the AM-GM relation. Remember that the arithmetic mean AM is always greater than the geometric mean, that is GM. And we'll just do it for two numbers, suppose a and b, which are in positive real plane. So the arithmetic mean of a and b becomes a plus b upon 2, and this thing is always greater than the geometric mean, that is square root of ab. Okay. Now I will simply divide both of the sides with square root of ab. So I will get a plus b upon 2 divided by square root of ab is always greater than or equals to 1. ab upon square root of ab becomes simple times 1. Okay. So after we divide both the sides with square root of ab in this equation, we get that a plus b upon 2 upon square root of ab is always greater than or equals to 1. Now over here I will do a substitution. Suppose like this way. We have a plus b upon 2 divided by square root of ab means multiply square root of ab. This thing is greater than or equals to 1. Okay. So what if I equate this thing as a variable k and give k the particular boundary that k is always greater than or equals to 1? All okay. This particular fraction would always be equals to k, where k is either 1 or a value that is greater than 1. Simple. So we got this thing over here with boundary for k that k is always greater than or equals to 1. So from this particular relation I can get that a plus b is equals to 2 times k times square root of ab, where k is always greater than or equals to 1. Remember this thing, okay? So this was the final equation at which we stopped. Then we saw the AMGM relation and got this equation that a plus b is always equals to 2 times k times square root of ab, where k is greater than or equals to 1, okay? So remember this particular equation. In this we have a plus b. So this a plus b can be just replaced with this value that we just got. So the equation will look like the bracket as it is square root of a plus square root of b getting multiplied with, now instead of ab we can put this value, that is 2 times k times square root of ab, okay, minus ab, and this thing is getting divided by square root of ab, okay. Now one thing I forgot, that as we can see that here we have b and a in the denominator part, so a and b belongs to the positive real plane but not equals to 0, remember that, okay. So square root of a plus square root of b getting multiplied with this thing divided by square root of ab. Now as a and b are not equals to 0, their product would also be not equals to 0, and this means their square root is also not equals to 0. So this and this can be easily factored out, no problem. So what we finally get is square root of a plus square root of b getting multiplied with 2 times k minus 1. Okay, we got this thing, and remember that k has a value greater than or equals to 1. Now look carefully at this particular bracket, that is 2 times k minus 1, 2 times k minus 1. Now for k is equals to 1, the value for 2 times k minus 1 is going to be equals to 1, okay. Now we will take the second case, that k is greater than 1. Remember the boundaries, that k is greater than or equals to 1. K equals to 1 we have done, now k greater than 1. So what we have to take is 2 times k minus 1. Now 2 is getting multiplied with k, and remember that if a number a is multiplied with another number b and b is greater than 1, this whole product would always be greater than the number itself, that is a. It's a very simple thing. Like if 5 is getting multiplied with 1.1, the answer would be 5.5, that is greater than 5. So remember this particular thing, that if a is multiplied with b is greater than or equals to 1, this complete product would always be greater than or equals to the number itself a. And if b is smaller than or equals to 1, then the product a into b would always be smaller than or equals to the number itself, okay. Now take another example like 6 into 0.5, the answer would be 3, and that is smaller than 6. 6 into 1.2, the answer would be 7.2, and that's greater than 6. So you can see that if we take any number that is greater than 1, the value for that product will increase, and if we take any number that is less than 1, the value for that product will decrease. So the same thing is over here. 2 is multiplied with k and k is greater than 1. This means the value for the product 2 times k would always be greater than 2, that is the number itself. So the next thing we have is minus 1. So 2 times k, I will subtract negative 1 on both of the side in this equation. So 2 times k minus 1 would always be greater than 2 minus 1, that is 1. So here instead of equals to sign we have to put that 2 times k minus 1 would always be greater than 1 for k greater than 1, okay. So with the boundary for k, that k is greater than or equals to 1, we got that 2 times k minus 1 would always be greater than 1 or else equals to 1. So let me write down the final thing. So as per the working that we just saw, for k greater than or equals to 1, the value for this complete bracket would always be greater than or equals to 1. So 2 times k minus 1, I will just take it as another variable m. So what I get is m greater than or equals to 1, that is ultimately the boundary for 2 times k minus 1. So this equation will now turn out to be square root of a plus square root of b getting multiplied with m, where m is greater than or equals to 1, okay. Now the thing that we just discussed, a number a multiplied with another number b, if b is greater than or equals to 1, the value for this product will always be greater than or equals to the number itself, that is a. The same thing is over here. This number is getting multiplied with m. m is greater than or equals to 1. This means the value for this product would always be greater than or equals to the number itself, that is square root of a plus square root of b. So we get this thing over here. So here we have this particular inequality. Now remember that this particular thing, square root of a plus square root of b into m, is ultimately square root of a plus square root of b into 2 times k minus 1. And this thing is ultimately this thing was this we got from here, and this thing was finally equals to a upon square root of b plus b upon square root of a. So this thing is ultimately the modified form of a upon square root of b plus b upon square root of a. So we can just replace this thing, and this thing is always greater than or equals to square root of a plus square root of b, and that's the answer that we were looking for. Remember, this was the inequality that we have to prove. Okay, now what I'm telling is, listen carefully, that I have never been taught in school how to solve this inequality problem, so I don't know a very kind of perfect steps or like this way. This is the first time I am trying to solve an inequality, so I like to see if my method is correct, if this way is correct or not. I think it should be correct, but you viewers can tell me better in the comments. So this was my way, and I am still doubtful if this method is correct or not, because I have never been taught how to solve this. It's just from my side. Okay, so do let me know in the comments if this method is correct or not, and if you have any other method by your side, you can also comment below. And if it's hard to comment, you can email me, or else you can send it to me on my Instagram. The link is in the description.